Economists and biotech engineers now treat aging as a systemic flaw, a biological bug on the verge of crashing the global economy. By 2050, the demographic makeup of advanced economies will shift. In nations like Japan and South Korea, 30 to 40% of the population will be over the age of 65. This demographic transition has prompted the International Monetary Fund to sound the alarm over long-term fiscal sustainability. This table identifies the specific fiscal costs. The IMF projects that aging-related health spending will increase by 2 to 6% of national GDP by 2050. Projections suggest this shift will further reduce annual GDP growth by 0.3 to 1.2 percentage points by 2035. Conventional policy instruments have failed to close the elder care workforce gap. Under our current biological trajectory, the rising cost of care is becoming a primary threat to economic stability. Modern medicine has successfully extended the human lifespan, yet those extra years are rarely characterized by health. The gap between lifespan, how long we live, and health span, how well we live, is widening. Globally, individuals now spend nearly a decade of their lives managing chronic conditions and declining mobility. The biological driver behind this decline is the accumulation of senescent cells. When normal cells are damaged, they typically repair themselves or undergo a programmed death. Senescent cells do neither. These damaged cells evade the body's clearing mechanisms. Instead, they linger and secrete inflammatory molecules that compromise neighboring healthy cells, triggering chronic diseases. This decade of cellular toxicity is a primary root cause draining healthcare resources. It turns the final years of life into a period of extreme economic and biological strain. This chart tracking global financial shifts shows the scale of the reaction. By 2026, the global longevity economy is projected to scale to $33 trillion. Venture capital is flooding into startups like Noom, Ro, and Pharmeasy as they pivot toward treating age-related decay as a manageable medical priority. Tech entrepreneur Brian Johnson has become a public figurehead for Healthspan optimization, spending roughly $2 million annually to slow his biological decay. His regimen involves strict nutrition schedules and pharmaceutical interventions designed to ensure that his body's repair processes keep pace with his cellular breakdown. While individual biohacking gains public attention, the systemic solution required by the economy lies in the broader application of cellular reprogramming. Researcher David Sinclair describes the human body as an epigenetic operating system. In this framework, biochemical markers that regulate our genes can potentially be adjusted to move the biological clock backward. This approach, known as partial epigenetic reprogramming, restores damaged cells to a younger state by modifying these markers without changing the underlying DNA sequence. Life Biosciences is using this technology to develop ER100, a therapy that uses 3 specific transcription factors to regenerate neurons in the eye and preserve sight. In early 2026, the FDA cleared ER100 to begin phase 1 human clinical trials. This milestone provides the first regulatory path for evaluating whether cellular rejuvenation therapies can safely transition from the laboratory to human patients. Biological treatments will take years to complete clinical trials. Healthcare systems require immediate technological infrastructure to manage the aging populations they have today. This is the role of agentic AI. These autonomous systems can coordinate multi-step workflows, such as detecting clinical deterioration from home monitoring data and automatically initiating follow-up care. This case study on institutional readiness highlights Singapore as a benchmark for transformation. To address a rising dependency ratio, the government has integrated national digital infrastructure with a layered, preventative financing model. Success in these environments depends on institutional design. Breakthrough science cannot stabilize the system without the governance and digital infrastructure required to deploy it. This approach to the aging crisis combines 3 prongs: cellular reprogramming for biology, agentic AI for logistics, and multi-trillion-dollar capital for scale. Delaying the onset of chronic disease allows individuals to remain active during years typically spent in medical care, potentially offsetting the massive costs of the demographic shift. However, current socioeconomic stratification risks limiting these gains to the most affluent populations. If deployment does not prioritize underserved groups, the health span gap will become a driver of deeper inequality. With these first human trials underway, biological aging is being reframed as a manageable engineering challenge, one that global economies are now racing to solve.